Hello everyone, I am Brigurish Mishra, a PhD student at IIT Bombay, and this is week 5 of Biophotonics. So in this live interactive session, we will discuss the assignment questions of week 5. I mean, although the answers are already there, but we will discuss about the questions given in the assignment. Okay, so in week 5 mostly laser, the operation of laser application, and the principle of laser is discussed, along with different type of laser, for example non-linear laser discussed. So the questions are based on those stuffs. So let's start. So the question one is, which of the following phenomena is involved in the operation of laser? So stimulated emission, spontaneous emission, absorption, and the option D is all of these. So if you have gone through the lectures, you would have known that these all three options are included in the operation of laser. So the correct answer is D, all of these. So let's start little bit about this stuff. So the main principle of laser, what is it? Is to convert electrical energy into very high energy density beam through all these processes. Okay, so principle of laser is to convert electrical energy into a high energy density beam of light through stimulation and amplification. Okay, so all these processes are involved: absorption, spontaneous emission, and stimulated emission. So let's discuss all these processes in a little bit of detail. So the first one is absorption. Okay, so suppose I have two energy level E1 and E2, and I have an electron at the lower energy level E1. So suppose an electron, and not electron, a photon. Okay, a photon with incident energy delta I, this is equal to the difference in energy of these two levels, upper level and lower level, E2, E1. Okay, so this photon energy is absorbed by this, you can call it electron or atom. Okay, at this state, and this excites this atom to the next level, E2. Okay, so this absorption excites the atom to go into next level, higher level, E2. Okay, and similarly, after absorbing this photon, the atom goes to the higher level, and after a little bit of time, very little, in nanosecond or even lesser, okay, this electron or atom spontaneously emit or radiate the photon of the energy. Suppose again the energy levels are E1 and E2. So E2 at higher level, E1 at lower level. So this atom goes back to its lower state by emitting an photon of the energy delta E, which is E2 minus E1. Okay, so this process is known as spontaneous emission, because it happens spontaneously. Okay, so here for the case of absorption, photon with energy delta E is absorbed by atom, and by atom at E1 state, by atom in state E1, and it excites to next level E. Okay, whereas for the spontaneous emission, this excited atom can de-excite to a lower level if there is a possibility of vacant site available. Okay, so in this process, photon of energy delta E is released. Okay, so now we'll talk about the third process, which is known as the stimulation. Okay, or stimulation, yeah, so stimulation emission, or you can say stimulated emission. So stimulated emission. Okay, so few properties of the stimulated emission is it is not dominant, it is not very dominant process at room temperature. You need a very high temperature for stimulated emission, and also the main thing is it is very important for laser. Okay, for laser. So what is it? So suppose I have a photon. Okay, suppose let's say this the atom here at higher level. Okay, it is not spontaneously emitted, so emitted photon. So suppose our atom is at excited state E2. Okay, and the energy difference between E2 and E1 is E2 minus E1 delta E, and sent a photon of energy delta E, which is E2 minus E1. So what happen is this photon of energy excites this this atom at higher level without getting absorbed by this atom at level E2. So this excitation causes this atom to uh, go to de-excite itself and go to level E1 and releasing a photon of same energy. And since this photon of energy delta E is not absorbed by this atom, it only excites the atom at E2, but it didn't get absorbed by this atom at E2. So we will have this incident photon also. Okay, so in this case we have two photons, and this stimulated photon, this stimulated photon also has the same energy. Okay, same energy equal to the incident energy of incident photon energy. Okay, so this is the stimulated emission process. So atoms in upper energy level E2 can be triggered or excited by an incident photon. The energy of the incident photon must be equal to the energy difference between upper and lower state of atom. Okay, and the most important thing is atom should not absorb this incident photon. Okay, so this stimulated photon with same energy also travels in the same direction as the incident photon, and also is in the coherent state with the incident photon. Okay, so the stimulated photon travels in the direction same as incident photon. Both are in same phase and have same wavelength. Okay, this is the important property of the photon. That's how we get the amplification. So amplification is mainly due to the stimulated emission. Okay, that is why we have very high energy density beam in the laser. Okay, so question 2, statement 1, stimulated emission can happen between any two upper and lower energy level. Stimulated emission is responsible for amplification and is highly coherent. So we just discussed about it, so both the statements are correct. Okay, so it can happen at any two upper and lower energy level. So depending upon this difference, we have laser light with a different wavelength, different frequency. Okay, and yes, as just said that the stimulated emission is responsible for the amplification, and it is highly coherent with the incident photon, okay, of same energy. Question 3: which of the following are components of optical cavity? So pump, mirrors, active material, all of this. So if you remember the lecture, the optical cavity is the portion where this laser process happens. Means you have a pump which sends the incident photon, and then you have an active material where absorption, spontaneous emission and stimulated emission occurs, and then we have a mirrors at both the sides which restricts the photon movement inside this inside these walls, and that's how we have more number of photons with the same frequency, same wavelength, and the density of photons is very high. So that entire region is known as optical cavity resonator. So all these three components are present in the optical cavity. So the correct answer is D, all of these. Okay, so for laser action we need to confine photons in the system to allow number of photons created by stimulated emission to exceed all other mechanisms. All other mechanism means stimulated emission should occur before spontaneous emission. So we need to have higher stimulated emission compared to the spontaneous emission. Okay, so this is achieved by bounding the laser medium between two mirrors. It contains a pumping source which provides photons with specific energy to the system and an active material in which absorption, spontaneous emission and stimulated emission occurs. This complete system is called optical resonator cavity. Okay, so next move to the next question, which is question 4. So why do we need a metastable state? Okay, so what is a metastable state and where does it present? First let's know about that. So metastable state is present in a 3-level system, 3-level laser system, or you can say 3-level laser. So what is metastable state? It is an excited state of atom. Okay, so it is an excited state of atoms. What kind of excited state? So initially material is excited to a short time high energy state that spontaneously drops to a somewhat lower energy state with long lifetime. Okay, so this state is the metastable state which has long lifetime. Okay, now why it is very important? So metastable state is very important for 3-level laser because it gives the stability. Okay, and it also helps to increase the number of photons. I mean, that means to build up the population inversion, and also the most important thing is it traps and holds the excitation energy. Okay, so the correct option is all these 3 things. We need a metastable state to achieve stability, to build up population inversion, and to trap and hold the excitation energy. Okay, now the next question is the amplifying medium of a helium neon laser has an amplification spectral band equal to 1500 megahertz at 632.8 nanometer. What must be the length of the laser cavity to ensure that only one longitudinal mode oscillates? So if you have gone through the lecture, there is a formula given to calculate the length of the cavity. which is L equals to mc by 2 nv. Now here in the question it is saying that one longitudinal mode oscillates. One longitudinal mode oscillates. So what does that mean numerically? That means we have to take m equals to 1. Okay. Also consider medium air from where pumping is happening. Okay, medium is air, that is n equals to 1. Frequency is given, this is nu, let's write it correctly. Okay, so frequency is given, nu equals to 15 megahertz, that means 1500 into 10 to the power 6 hertz, or I can say 1.5 into 10 to the power 9 second inverse. Okay, so and the last one is c, speed of light. Speed of light c equals to 3 into 10 to the power 8 meter per second inverse. So the length of cavity is 1 into 3 into 10 to the power 8 by 2 into 1 into 1.5 into 10 to the power 9 meter. Okay, meter will be the unit because second inverse and second inverse will be cancelled out. So this is 1 by 10 meter or 0.1 meter. Okay, so the right option is option C, 0.1 meter. Let's go to another question. Question 6, SHG. SHG means second harmonic. Okay, second harmonic generation. So SHG of a laser light source at a wavelength of 1064 nanometer will occur at. So what will be the wavelength of the laser's light source? Okay, I mean what is the wavelength of a second harmonic generation when the laser light source is at wavelength of 1064 nanometer. So what is SHG? Okay, so it is also known as first let's write SHG, it is second harmonic generation. So it is also known as frequency doubling. Okay, this is the important term to remember. Frequency doubling means it doubles the frequency. Okay, so doubles the frequency means half the wavelength. So in this process an input wave generates another wave with twice the optical frequency in the medium. Okay, so twice the frequency, means half the wavelength, or I can say half the vacuum wavelength. Okay, half the vacuum wavelength. So suppose I have a non-linear crystal here. Okay, this is so it only happens in non-linear crystals. Okay, this second harmonic generation. So let's say pump wave of wavelength 1064 nanometer. Okay, so and pumping, and the output is the residual pump plus second harmonic wave of wavelength half of the incident one, that is 532 nanometer. So the correct answer is C, 532 nanometer. Okay, so let's move on to the next question number 7. So statement 1, SHG is an anisotropic property. In SHG, the wavelength of output light is half of that of input light, and the frequency is also halved. So we just discussed that SHG is only happening in non-linear crystals, so of course it is an anisotropic property. So statement 1 is correct. Okay, so statement 2, in SHG the wavelength of the output light is half of that of the input light, and the frequency is also halved. So the first part is correct, but second part, that is frequency is also halved, is incorrect. So that means statement 2 is incorrect and statement 1 is correct. So correct option is option C. Okay, so question number 8, which of the following lasers is used in photodynamic therapy? So what is photodynamic therapy? Photodynamic therapy is defined as an oxygen dependent reaction between a photosensitizing dye and light. Okay, the wavelength of light chosen were based upon the absorption spectrum of the system. So in this case, system is our body organs, so generally it is 400 to 800 nanometer wavelength visible light. Okay, so generally, so as mentioned here, photosensitizing dye, so you need a dye which sensitizes to the light. So generally dye laser is used. Currently diode laser is also being explored, but dye laser is used in the cancer photodynamic therapy and all. Okay, so yeah, it's done. So question 9, virtual energy states are imaginary unobservable states. The concept of virtual energy states violates Heisenberg's uncertainty principle. So first let's know what is this virtual energy state. So due to Heisenberg energy time uncertainty principle, a photon can be absorbed without conservation of energy as long as it is emitted a short time after. Okay, a short time after means it doesn't stay for too long. This process is called virtual absorption. Virtual absorption, and the shortly lived, that means virtual excited state is called the virtual or intermediate state. Okay, now the important thing is although uncertainty principle allows them to come into existence, but it also dictates that they cannot be directly observed. Okay, so that means both the statements are correct. Okay, that is virtual energy states are imaginary unobservable states, and also that the concept of virtual energy states violates Heisenberg's uncertainty principle, although it is originates due to Heisenberg uncertainty principle. Okay, so both the statements are correct. Option A. The question 10, which of the following procedures requires an endoscope? So what is an endoscope? And endoscope is a device with a light source attached it is used to look inside human body. Okay, so this is required when you have to looking into human body, so that is known as biopsy. Okay, so you need endoscopy in biopsy. So yeah, that is all for today. So we will discuss, so we will meet in the next Friday with the week 6. Okay, thank you.